So far, we have done quite a number of examples with the same specifications and details of the column, only when the conditions are different. In the sub-question F, we deal with short column, where the moment is acting in the major axis, whereas in the sub-question G, we deal with unbraced slender column with the moment acting in the major axis. Later in sub-question H, the column is unbraced and slender. The moment is acting in the minor axis. And then in the following sub-questions, unbraced and slender column with the moment acting in the minor axis. What you see here, the differences in terms of the combinations between short and slender column, braced and unbraced column, as well as the moment acting in the major and the minor axis. All this can lead to a lot of different combinations. We only discuss about 4 among those combinations. There are many other more. For example, short column having the moment acting in the minor axis, and probably braced slender column with the moment acting in the major axis. You can try on your own. These 4 conditions here is sufficient for us to grasp the pattern in terms of the design calculations. And this is the purpose of this sub-question. The sub-questions ask us to compare the design outcome for the 4 load cases and then state your finding. To answer this, you will have to look back the calculations process for that 4 sub-questions, and then I have worked out the summaries. For the same set of loading, axial loops are the same, the moments are also the same, only that the directions of the moments towards the major or minor axis differs, and then the conditions of the columns are different. The different loop conditions shall give you different design outcome. As summarized here, let us deal with them one by one, and hopefully by comparing those designs, you can grab some understandings from different types of the column, as well as gain some ideas in terms of the design process associated to different loop conditions. First is about the H that we use in our calculations. Remember, in the calculations process, there are equations requiring the H. For example, E naught, you need the H here. For example, calculating the effective depth, you also need the H here. And also calculating the x-axis of the design chart for the column, you have to be careful with the H square. You need to choose the right value, especially when the columns is in the rectangular shape. Getting the wrong H, it will lead to you mistakes in terms of the calculations. This may seem to be complicated, but the principles is simple. For a typical rectangular column, we look at the directions of the moment, whether it is acting in the major axis or the minor axis. If the moment is acting in the major axis, the H, it will be the larger width of the column. In contrast, when the moment is acting in the minor axis, that means your H now, it will be the shorter width of the column. I guess by now, it shouldn't be confusing to you. There's only one principle to decide the H. Next, we talk about M2. You see the calculated M2 here are different. If you observe the calculations, the M2 is largely governed by the L0, which is the effective length. Also within the equations that you use to get the K5, you need the slenderness of the section. Because of these two, the M2 is not the same for different loop conditions. Now you might want to ask, why are these two different? This you will have to refer back to the calculation steps to determine the slenderness ratio. More specifically, it is due to the equations L0 being used. Due to different L0s, now you will have different slenderness ratio. And if you look at the summaries between the braced and unbraced structures under the same conditions, the L0 differs significantly between braced and unbraced structure. They also vary in terms of the major and the minor axis. Due to the variations in terms of the radius of gyrations between the major and the minor axis, your slenderness ratio also differ quite significantly. Now that your L0 differs, your slenderness differ, then you will get different M2. Another important observations regarding this M2 is that this M2 is actually the second order moment. There is no second order moment for the short column, but you will need the second order moment for the slender column. That's why when you deal with the slender members, there will be M2. And then if you observe on the calculation steps, all the slender column will have something in common, where you're going to start with assuming the KR, because at the moment you don't know the amount of reinforcement. And then later from the design chart, you calculate the AS required. Only then you substitute into the equations for omega, and subsequently you calculate the KR. Compare your KR with the one that you have assumed earlier on. If the KR is the same as what you have assumed, that means your second order moment M2 is confirmed. If the KR assumed and the KR calculated are not the same, then you will continuously test the KR by substituting with the new AS as calculated from the design chart. The process will continue until you reach to a constant KR and where you can confirm your M2. This is about the M2. And then you also observe the calculations for the MOE. In fact, MOE is actually the first order moment. Supposingly, you need to calculate the MOE for all cases. However, if you observe the calculation steps and observe the equations that giving you the MED, only braced structures will require the MOE. The MOE for the unbraced slender column and also for the short column is not likely to be the critical moment. You can choose to calculate the MOE for these two cases, but it will be a waste of effort and time. Eventually, you're not going to use it. That's why you can choose not to calculate the MOE for the short column, as well as for the slender and unbraced column. You only need it for the slender and braced column. Next is about the MED. The MED here, it will be purely due to the first order moment. Whereas when you deal with the slender column, the MED shall be also governed by the second order moment, which is the M2. It is also possible that the first order moment is still the most critical for slender and braced column. since the MED is governed by 4 parameters here. The biggest value shall be the MED. If the first order moment alone is greater than the rest, then you may use the first order moment. This does not apply to the embrace structure. Because the MED, it will be the summations of the first order moment plus the second order moment. Ultimately, because of these relationships, you will expect that the embraced slender columns is going to be most critical. Not to mention when we are talking about the bending in the minor axis against the bending in the major axis. Because of different MEDs that give you different AS required. AS means no change, the same equations being used, same requirement. AS maximum also no change, similar 4% limit, and at the lapping regions 8% limit. And then because of the AS required, the reinforcement bar required changes. Embraced slender column with the moment acting in the minor axis will have the most amount of reinforcement bar required. Short column with the moment acting in the major axis will be the least critical as implied by the AS required. You will see the area of reinforcement bar required increases over different load cases. And then the shellings, it will be the same. No change since they are referring to the same set of requirements. By comparing the calculated results side by side, there are a lot of understanding that you can acquire. First, you know that the short column is actually less critical than the slender column. You may compare the short column against the slender column. In terms of the amount of reinforcement bar required, slender columns always require more reinforcement, even though the same amount of loading acting onto the column. This gives you a good understanding when it comes to the design of the column. If you have the intentions to make the design more economical, you can consider manipulate the slenderness of the column. Try to make it as the short column. Then, by increasing slightly the dimensions of the column, changing the column from slender to short, not only you can reduce the amount of reinforcement bar required, the calculation steps also become simpler, since you do not have to calculate the second order moment, and you do not need to go through the trial and error process, assuming the KR first, and then coming back to verify the KR. This is going to save you a lot of time. So, if you can, maybe you should go for the short column. Unless, under certain practical considerations, you cannot make it short column. For example, in the industrial practices, sometimes the architect specified the size of the column, or sometimes you will need to hide a column within a wall, which is not anticipated by the architect. You can choose to add the column in the wall, but the column should not appear, should not be seen. Under these circumstances, then you have no choice, then go for the slender column. Now, if you go for the slender column, you're going to expect you're going to need more reinforcement bar in the column. Next, if you compare the result from the braced column and the unbraced column, it seems that unbraced column, it will be more critical. Let's say you compare these two. The same set of loading, same axial load, same moment, both acting in the minor axis. Now the calculated outcome differs. You will need more reinforcement bar for the unbraced slender column. Why is it so? This can be seen from the equations to determine the MED. The MED here, it will be the summations of the first order and the second order moment. Whereas this one, it does not require to be added up with the second order moment. In the case that the second order moment is used, it is anticipated happening here. That means the second order moment does not go along with the N02 in the brace structures. Because of this, the design moment for the brace structures is less critical than the design moment for the unbraced structure. This is about the second point. Next, the moment acting at the major axis is less critical than the minor axis. Let's say you compare these two. They are both unbraced and slender column. The loadings are the same. Only the moments for these questions is acting in the major axis, whereas this one is for the minor axis. The AS required changes quite significantly. It may seem to have little increment in terms of the moment that you use to design for the reinforcement bar, but you know that the column is more critical due to the moment. This slight increments leads to quite a significant increments in terms of the amount of reinforcement bar required. Here you only require 4H12, but here you require 4H16 plus 2H12. Quite a significant jump in terms of the amount of reinforcement bar provided. Next, the MOE we have mentioned already. It is only required when dealing with the brace and slender column. Now, if you want to simplify your calculation steps, if you are dealing with the short column or unbraced slender column, regardless it is acting on the major or the minor axis, you can skip the calculations for the MOE. Another thing, it will be the H, which is governed by the directions where the moment is acting. If you are dealing with the major axis, your H will be the bigger value of the column dimension, which in this case is 300. Now, if the moment is acting in the minor axis, it goes with the smaller column dimensions, which in this case is 150. Lastly is about the serviceability requirement. This serviceability requirements such as AS min, AS maximum, maximum spacing, minimum bar diameter, minimum numbers of reinforcement bar, and etc. They are universal to all columns, regardless of their types and the conditions. I believe after you have gone through these 4 questions here from the videos that we have covered previously, and then after going through the comparisons of the design outcome, you will have gained something fruitful. Especially these findings can help you to make good engineering decisions when come to the design of the column.